Hello, chemistry students. Here is a correction for ChemQuest number 5, the numbers in chemistry one. So, information qualitative versus quantitative. The following observations are qualitative. The building is really tall. It takes a long time for me to ride my bike to the store. I live really far away. The following observations are quantitative. The river is 31.5 meters deep. The cheese costs $4.25 per pound. It is 75 degrees Fahrenheit outside today. Number 1. What is the difference between qualitative and quantitative observations? Your answers should reveal an understanding of the definitions for qualitative and quantitative. So notice in these qualitatives, we're really just looking at the qualities. Versus here we're looking at a quantity, and then a quantity, remember, is an amount. So notice that our quantitative measurements all have a number and units in them, while our qualitative do not. So qualitative, describes the properties. So again, that building's tall, or it takes a long time, or I live a long ways away. Okay. Whereas quantitative will use numbers and units. Okay. The person who wrote this ChemQuest explained it this way. Qualitative refers to the general quality of a characteristic, tall, short, long, wide, etc. Whereas quantitative includes the quantity of the characteristic, how tall, how short, how long, how wide, etc. Therefore, quantitative observations will always contain a number to specify more precisely than qualitative. And both of them are quite useful in chemistry, right? But we definitely will be dealing with a lot of quantitative measurements this trimester. Number 2, write an example of a quantitative observation that you may make at home or at school. Okay, so for example, there are 35 desks in the classroom. Okay. And again, there are lots of different examples of that. The person who wrote this explained, I like to eat 2 bowls of cereal each day. My shoes are size 10. Okay, so anything that involves a number works there. Why are instruments such as rulers, scales, balances, thermometers, etc. necessary? Well, we need these instruments because we need to be able to measure these quantities. And also important is we want to make sure that no matter where we are in the world, that our unit is always the same. So it also helps us make sure that if I'm talking about a meter here in the United States, that it's the same. A meter is the same length in Japan or Germany or everywhere else in the world. Again, the person who wrote this explained it this way. Instruments help us to communicate with each other effectively. Without instruments, we could only speak in generalities. They also make it possible to know the exact quantities. So again, communication is an important part of our instruments as well. So we see a table here about units. The following tables contain common metric or SI units and their prefixes. Table 1, metric base units. So we have length, the meter, and its symbol is a lowercase m. Mass, a kilogram, and its symbol is a lowercase k and g. Time, second, an S. Temperature, Kelvin, a capital K. Volume, a liter, a capital L, and amount of substance, mole, abbreviated MOL. So our next table is about prefixes for the metric base units. Okay, and you see them here. And then it says, note the following examples. Milli means thousandth, so a milliliter, symbol ml, is 1,000th of a liter, and it takes 1,000 milliliters to make 1 liter. Mega means million, so megagram means 1 million grams, not 1/1,000,000th of a gram. 1/1,000,000th of a gram would be represented by the microgram. It takes 1 million micrograms to equal 1 gram, and it takes 1 million grams to equal 1 megagram. 1 centimeter is equal to 0.01 meters because 1 centimeter is 1/100th of a meter, and 0.01 meters is the expression for 1/100th of a meter. So this is useful. I typically, and when we take notes, we'll kind of put it this way. Okay, and eventually we'll have this in our notes, but you might want to jot it down right now too. So this is the metric system, okay? And this base, this is kind of what we were talking about actually here, okay? When we talk about kind of the base, for length, that base is a meter. For mass, that base is a gram. For time, that base is a second. For volume, that base is a liter. Okay, so base is kind of generic depending upon what you're measuring, what kind of quantity. And this is deca, hecto, kilo. These little lines in here are important because remember the metric system is all based on factors of 10. Okay, so these are factors of 10 that we don't typically deal with much. And then this is mega, which is this one right here. Smaller than our base, we have deci, centi, milli. Two that we don't deal with much, here's our micro, nano, and pico. And I like it this way, and we'll kind of use it this way in just a couple minutes when we start to look at these, and I'll kind of explain how we use it. I prefer it this way because I know back in middle school that you learned to just write it left to right, and then you moved decimal places. But you're at a point, being a college prep chemistry student, that we shouldn't just be moving decimal places. In middle school, your teachers thought that perhaps some of the students in your class couldn't understand that when we move our decimal to the right, it's because we're multiplying by some factor of 10. And when we move our decimal to the left, it's because we're dividing by some factor of 10. They truly thought that some of the students in your class, and probably rightfully so, wouldn't be able to understand that. But you're sophisticated students, you're going to college, you're continuing your education after high school, and so we're at the point where we can't just be moving our decimals. In addition, our problems in chemistry eventually are going to get difficult enough that we're going to have to be able to do more challenging problems. So we're going to use this in just a couple minutes. Like I said, you might want to jot it on the side of your ChemQuest. So question number 4 asks us, how many milligrams are there in 1 kilogram? So this is saying if I have 1 kilogram, I want to know how many milligrams that is. So we're going to do something that's called dimensional analysis. In dimensional analysis, we always start with our given. And I don't ever write it as over 1, but you technically could write it as over 1. Now, we're going to treat this like our units, the dimensions, okay, are algebraic letters, and I want them to cross out. So if I want kilograms to cross out, it has to go in the bottom or the denominator. I call them bottom and top because I can never remember if they're the denominator or the numerator. Okay? And I want to change this to milligrams, so I'm going to put milligrams on the top. And I can do that because they're both grams. So kilograms are going to be crossed out. I'm going to be left with something in milligrams. Now, here's the part where this comes into effect. So what do I put for numbers here? Okay, I don't like tiny little numbers, right? You know, I I was not a strong math student growing up, okay? So I always want to make this the easiest. So I look at these two and I say, which one's larger? Well, here's my kilo and here's my milli. So my kilo is larger. So because kilo is larger, I'm going to make it 1. Now I need to figure out how many milligrams it is, so I'm going to do 10. And then I'm going to put an exponent up there. And the exponent I'm going to put up there is going to depend on how many times I move now. So to go from kilo, I'm going to go 1, 2, 3, 4, 5, 6. I move 6 times. So this is going to be 10 to the 6th. So my answer for this is 1 times 10 to the 6th milligrams. Okay? Which also means I can write a 1, right, with 6 zeros after it. 1, 2, 3, 4, 5, 6 milligrams. Either way is fine, okay? But this is how I want you to show your work for these problems. So, number 5. How many meters are in 21.5 kilometers? So 21.5 kilometers, we want to know how many meters that is. So again, I'm going to start with my given, which is the 21.5 kilometers. Kilometers is going to go on the bottom because I want it to cross out. And I'm going to put meters on the top because that's what I'm trying to convert to. And I can do that because meters are a unit of length, just like a kilometer is. Again, the question then is, which one is larger? Here's my kilometer. My meter is one of my bases, so my kilometer is larger. So I'm going to make it 1, 10, and now I'm going to figure out what that number is. And to figure out that number, I do the same thing. So I move 1, 2, 3 times, so my exponent is third. Now, that means that my answer to this is 2.15 times 10 to the 4th meters, or I can take 21 and then I'm going to add kind of 2 zeros, and I have 21,500 meters. Now, here's the deal. No shame in using your calculator for these. Absolutely none. When I was in high school, I would have pulled out my calculator, right? And I would have done 21.5 times 10 and caret third, and I would have gotten my answer. I never could have done this in my head. I can do this in my head now because I've been doing it a long time, and it makes sense to me. But in high school, it didn't. So I'm just telling you, there's no shame in this. If you want to use your calculator to do these, that's fine. All I care about is that you get the correct answer at the end and that you're able to show your work the way I'm asking you to show your work. So number 6, is it possible to answer this question? How many milligrams are in 1 kilometer? Explain. So this is saying 1 kilometer is how many milligrams? Now, notice up here, remember I said we could do this one because this was grams and grams. We could do this one because it was meters and meters. But here I have meter, which is a unit of length, and I have grams, which is a unit of mass. What does that mean? That means that I can't do this problem, okay, because they're not the same units of measure. So, no, okay, because milligrams and kilometers are different units of measure. Okay, kilometer is measuring length, mass is measuring, or milligrams is measuring mass. So you can't do a problem where the units are not the same unit of measure. Number 7, what is the difference between a capital MM and a lowercase mm? Which is larger, one capital MM or one lowercase mm? Right? So what's the difference here? So it's kind of asking you to kind of come up here and figure this out, right? So a capital MM is a mega meter. My lowercase mm, right, that's a millimeter. So that's kind of what their difference is, right? So one's a megameter and one's a millimeter. Okay, and then which one is larger? Again, I kind of look over here, right? Mega is larger than milli, so the megameter is larger. So 1 megameter is larger. All right, next there's a little bit of review about scientific notation. So scientific notation is used to make very large or very small numbers easier to handle. For example, the number there can be written as 4.5 times 10 to the 16th. The 16 tells you that there are 16 decimal places between the right side of the 4 and the end of the number. Another example, 2.641 times 10 to the 12th. Again, the 12 tells you that there are 12 decimal places between the right side and the 2 at the end of the number. Very small numbers are written with negative exponents. For example, this number can be written as 3.78 times 10 to the negative 15th. The negative 15 tells you there are 15 decimal places between the right side of the 3 and the end of the number, right? You've learned scientific notation before, okay? This is just reviewing. So another example, okay? 7.45 times 10 to the negative 8. The negative 8 tells you there are 8 decimal places between the right side of the 7 and the end of the number. In both very large and very small numbers, the exponent tells you how many decimal points are between the right side of the first digit at the end of the number. If the exponent is positive, the decimal places are to the right of the number. If the exponent is negative, the decimal places are to the left of the number. Okay? So number 8. 2 of the following 6 numbers are written incorrectly. Circle the 2 that are incorrect. Okay? So when I look at these, and I think I'm going to have to try to see how this goes with zooming. I'll try that. Looks a little bit better. Okay, so 2 of these are written incorrectly. Circle the 2 that are incorrect. So 3.57 times 10 to the negative 8, that one's okay. 4.23 times 10 to the negative 2nd, that one's okay. This is one of the ones that's incorrect. Okay? And what's wrong with this one is this coefficient here, this has to be a number of 1 to less than 10. And this is not one of those numbers. So this would be the number 7530, okay, 7,530. So to write this in proper scientific notation, it should be 7.53 times 10 to the 3rd. 2.92 times 10 to the 9th is okay. This one, again, we would circle. Because again, my coefficient here has to be at least 1, but less than 10. Okay? So this really is the number 3.54. Okay? So to write this in proper scientific notation, it would be 3.54 times 10 to the 0. Okay? And then this one is fine as well. So what do you think is wrong about the 2 numbers you circled? C should be 7.53 times 10 to the 3rd. And E should be 3.54 times 10 to the 0. The correct format for writing numbers in scientific notation is with only 1 digit to the left of the decimal place. Also, the numbers should not begin with zeros. So again, these coefficients, which are our first numbers, have to be equal to or greater than 1, but less than 10. Number 9, write the following numbers in scientific notation. So this is going to be 2.531 times 10. And again, it's going to be a positive exponent because it's a large number. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 times 10 to the 16. This one should be 3.018 times 10. It's going to be a negative exponent because it's a small number. And 1, 2, 3, 4, 5, 6, 7, 8, 9 to the negative 9th. Write the following scientific numbers in regular notation. So again, this is saying take this and go 1, 2, 3, 4, 5, 6, 7. So I'm going to have a decimal, and then I'm going to have 1, 2, 3, 4, 5, 6 zeros. 8, 4, 1. For this one, because it's positive, I'm going to go to the right. So 1, 2, 3, 4, 5, 6, 7, 8. So 3, 2, 1, 5, and then I'm going to have 1, 2, 3, 4, 5 zeros. All right, information. Multiplying and dividing using scientific notation. When you multiply two numbers in scientific notation, you must add their exponents. Here are two examples. Make sure you understand each step. When you divide two numbers, you must subtract the denominator's exponents from the numerator's exponents. Here are two examples. Make sure you understand each step. Here's the deal, people. You're going to do this on your calculator. So what that does mean is that you need to know how to put scientific notation in your calculator. And for whatever reason, I've found that oftentimes students don't know how to do this. So when I'm going to put this number in my calculator, the best way for me to do that is to use this little E button. That E button takes the place of all of that times 3.2. And on this calculator, it's this button, right? It's the second button there, E36. And notice I get the right answer, 1.44 times 10 to the 40, this should be to the 49th. It's a typo on this, okay? So when I go and do this next one, and this is important that you know how to put this in your calculator. So if you don't have one of these calculators, whatever calculator you're using, it should have, and it's usually with this double E button, okay? So 5.9 E9 times 6.3 E, second E, E negative 5, okay? Now, here's one of those things where, right, you guys need to know that this is the same number as this, right? 1, 2, 3, 4, 5, right? That's the same number. And the way you can fix this on this calculator, second and degree, you can put this in scientific, in which case it's going to give you all your answers in scientific notation. So when we go down here and we do this next one, right, we're going to do 2.8 E14 divided by 3.2 E7, 8.75 times 10 to the 6th. 5.7 E19 divided by 3.1 E negative 9. And again, I get that same answer that it shows. Okay? So I don't expect you to remember how to do this, okay? What they're talking about here, I want you to be able to put those scientific notation in your calculator correctly. So number 11 asks you to solve the following problem. So again, I'm just going to use the calculator. Right, so 4.6 E34 times 7.9 E negative 21. Okay, and Right now, because this only has 2, I'm just going to use 2. So I get 3.6 times 10 to the 14th. Okay, we're going to talk about that here within the next week or so about significant figures. And realistically here, you should only use 2. So this next one, right, 1.24 e to the 12th times 3.31 e to the 20. And those each have 3 significant figures, so I'm going to use 4.10 times 10 to the 32nd. The next ones, again, same thing, right? So 8.4 e negative 5th divided by 4.1 e to the 17th. And these each have 2, so I'm going to make this 2.0 times 10 to the negative 22nd. Okay. Next one, 5.4 e32 divided by 7.3 e to the 14th. Again, just 2, so I'm actually going to make this 7.4 with my rounding times 10 to the 17th. Again, this next one, again, talks about how you add and subtract properly using scientific notation. Again, all I care here is you can use your calculator. Okay, so you don't need to do it this way. You just need to be able to put it in your calculator. So 4.25 E13 plus 2.1 E14 gives me 2.53 times 10 to the 14th. Okay. My next one, 6.4 e to the negative 18 minus 3 e to the negative 19th, and I get 6.1 times 10 to the negative 18th. Last one, 3.1 e to the negative 34th plus 2.2 e to the negative 33rd, and I get, I'm just going to use 2.5 times 10 to the negative 33rd. Okay, so again, the important part of this was about starting to learn how to set up those equations or those problems using dimensional analysis within the metric system. This scientific notation stuff, as long as you can use your calculator and know how to put it in your calculator, that's perfectly fine. Have a great day. Talk to you tomorrow.